So it's my great pleasure to introduce our next speaker, which is Davide Scaramuzza. Unfortunately, he couldn't be here in person, but he agreed to give the presentation remote, which is certainly also very nice to have. I know Davide since more than 15 years. I obviously know all his contributions, yet I took some notes to be sure not forgetting something. So Davide is professor and director of the Robotics and Perception Group at the University of Zurich. His main research interests are computer vision, robotics, and machine learning, and combining all those to do amazing things. He did his PhD at the ETH with Professor Roland Siegwart. He won various awards, among them an ERC grant and the IEEE Robotics and Automation Society Early Career Award. What's very nice is his work is also often featured in broader media, such as the New York Times, the Economist, Forbes, and other channels. He also serves as a consultant, for example, for the United Nations on disaster and crisis management, and he consults also various computer vision and robotics companies. He has co-authored and authored more than 100 papers in the field. He's a co-author of the book Introduction to Autonomous Mobile Robots that has been sold tens of thousands of times. He publishes in high-level conferences in computer vision and robotics. So when I met Davide about 15 years ago, I had the pleasure working with him in a European project. And back then he just finished developing the omnidirectional camera calibration toolbox. Oh, something is wrong. Back? Okay. So sorry, Davide, you are just a 10th speaker. I have to apologize today and yesterday for the technical problems. So I was at your contribution. So Davide worked on many things, and when I met him, he just worked on and finished the development of the omnidirectional camera calibration toolbox in MATLAB, OCamCalib. Probably some of you know it. I used it myself. Then he was already a pioneer in visual inertial odometry. He moved or extended his field of studies and research towards event cameras, where he showed various times what you can actually do with this interesting alternative signal to standard cameras. And then he moved towards learning agile vision-based flight. And if I'm remembering right, this is what we will hear from him today. So Davide, if it works for you, if we don't have any problem, then the stage is yours. But the slides are not the right ones. Oh, wait, sorry, give us a sec. Yes. Fred, this is not his slide deck. Just need to get your slides on the big screen, and then we are good.
What you just saw, it's the first AI versus human various competition we organized in summer of 2022, where for the first time, in the day I found a common speech of the story with all your vocabularies and the word combination, this is the world champions of the race. So the people that were actually talking about the world champions of the race. And the papers were published in Nature and also in Science Robotics. So the purpose of the dedicated to these two papers. But this is not just the work. This is the work of several great scientists in whom I had the pleasure to work over the past years. Actually, the work that I just presented was the result of 7 years of work and more than 12 years ago. But in particular, we started with scientists becoming these research fields. So, first of all, what is that we try to do in my lab? What I try to do in my lab is to try to understand what it takes to fly autonomous drones as good or even better than the human pilots. What we see in this video is not an autonomous drone, but it's a drone piloted by a human pilot. All the human pilots are navigator drones, vision-based. They put the camera on the drone that transmits the video, actually it's a full resolution, the doublets, and then the brain processes the information recorded by a normal camera, and well, the sends control commands to the fingers that basically act on the joystick. Now, what is interesting is that your pilots take 3 years to achieve the skills that you just saw in this video. Now, we thought that a lot of human pilots are simply because they were fast, and we were wrong. In fact, the average reaction time of the best human pilots is about a quarter of a second, 250 milliseconds. The thing about it is quite a lot of time, 150 milliseconds. That's a time when it takes to go from the latest receipt on the outputs down to the control commands on the serious. So is the process latency plus repeated response. How the measurement you have payment. You have quality the reaction time of extraction of crazy extraction pilots using hypercars. And basically this was published in the paper that you see here below service. Interestingly, our best perception and not based on the ends, so perception one of controlling rhythms, when we execute eight stimuli together, that are not in only 20 milliseconds. So our best autonomous vision-based algorithms are 10 times faster than experienced human pilots, but still human pilots beat and machine. Why? Because humans are supposed better than machines still nowadays to make decisions in complex situations. And this does not just apply. The drum body is only related to periods. There is not much that you can do with the humans unless you fly fast. Because if you can fly drones faster, then they can fly faster. So they can be more productive. Because they'll be over longer distances flipping and negative by the cabin. And this is not just speculation, it's the result of research. So what you see in this plot is on the vertical axis the distance covered by a drone in kilometers before the battery completely dies. And this plot was derived as a function of the flight speed in meters per second. And what you can see is that there exists an optimal speed. There exists an optimal speed that maximizes the energy for a given battery, for a given zone. Of course, I could, which depending on the drone mass, the aerodynamics, the number of propellers, but it always helps with standing over behavior. Now, where do commercial drone companies land on this quote? Well, they would be surprised to learn that actually the world leading their commercial drone companies are not thinking about that of the ultimate speed. With AI, fly build, stand build, they are world-leading companies being spectrum neurons, but they are flying at 3 calories slower than the optimal speed. So what this plot is telling us is what this mission will look like. In the future, I will draw all of you take 10 years, 20 years. In the future, we will add nodes that will be more agile than humans. And the reason why they will be more agile is to make their more productive as humans, so they can accomplish more living than the battery time. For example, the average inspection of a creature requires swapping the battery of the drone 50 times. If you can fly the band faster, you only need to swap the battery 5 to 10 times. And where the rockets planet, well, they're on the opposite side of this curve, because they're always not maximizing the rate of productivity, they are minimizing the net battery. Nevertheless, I believe that from unifying research, we can push the things on phones without main validation. And that's why we have worked with the past years to performance on this. Which applications will benefit from more agile drones? Many applications. First of all, such arrested because they are, any video that we can save can still rise. But also exploration and inspection. These are all applications where it's important to increase the productivity of the drones. Also, forest management. Nowadays, more and more drones are exploring to do the inventory of forests, to measure the diameter and the density of forests, to draw the perimeters of forests to avoid deforestation, and even to distinguish pipes. Also, personal care vehicles. Generally, there are 2 big companies for copper heating that are working to a professionalized field, passenger air transportation. And then we need to fly fast in order to increase the productivity on their transportation. And also space. According to NASA, NASA must sign its helicopter that will fly on Mars by 2030 and need to fly 20 hours. In order to do so, you will fly fast. But to fly faster, there are many challenges to overcome in terms of perception, learning, and control. Now, we are not the first to work on autonomous vision, on autonomous agile flights. We can actually plot the most seminal works or agile flight on 2 axes. One axis represents the agility, so how fast we're going to work. And the other axis, the reliance on the external sensor. Of course, if you want to get autonomous, you should rely on onboard sensor. So, our real work on agile flight was done by Peter Bill and Anglo NG at Stanford University in 2006, where they demonstrated that thanks to team personally for learning, they can control a quite big helicopter, the size to do acrobat maneuvers. But they relied on GPS and external antennas mounted on the ground. A few years later, Professor Rafael Andrea, together with his team, and also Professor Vijay Kumar, together with his team, demonstrated impressive acrobatic maneuvers thanks to the use of external natural capture systems. So these demonstrations are very useful because they tell us what ideal can be achieved, but this is the first localization, which means hybrid vector perception. But they only rely on external sensors, so they were not autonomous. However, in the last few years, there have been few works that need using onboard sensors in demonstrate agile maneuvers. But the amount of efforts that they achieve, the world of so agile as the ones achieved with external sensors. Whereas remote pilots, they're still agile, and they already rely on their own brain, even though they do not sit on the aircraft, because actually they use their works, but still they're super agile. What is the goal of my research? The goal of my research is to take this to the ends. Ideally, out the phone, you don't find so many tasks. We will job for this. But there are many challenges for vision-based agile aviation. The first challenge is the perception to action independence. So consider a phone that vision gets slow, that has canal enough. As you know, for a couple to mediate to the vision, it means to observe by texture. And it is very important, especially for steady signature. So if you do not have texture, the drone will crash. But we think it's very fault because it sets drones apart from the light robot and ground rollers in general. You see, any ground robot can remain with the seat of the wheels on the ground even when it purchases. But a drone that does not see can go slow. So this makes drones extremely difficult to navigate. And not only this, and very difficult is the fact to get perceptually touched around by the airport. In this example, you see the beacon is looking down at the yellow star. This yellow star indicates all the texture that the drone needs to observe in order to reach the destination. Now, you may know that the quadcopter, for example, is an underactivator with a plot. That means that if you want to reach a plot, you need to tilt the drone to orientate the vector perpendicular to the propeller blade towards the ball. But by doing so, you will lose the visibility of the texture that you expose the destination. And this will little graph. Now, this is a very simple example. But what this means, it means that you cannot do it in a binary perception way. But you need to create a series between perception and action. So you need to do all-import perception with a plan removal, where you plan trajectories that facilitate perception. That's challenge number one, very easy. Second of all, drones experience very large domain shifts compared to ground balls because they observe a steering from different reports. So you cannot just train a classifier to work from the same height. You need to train a classifier like YOLO or whatever you prefer. Some A also will be for the local to fly to. Third of its sensor means they are navigate fast and the road is the motion your and harder range. And this will cause the loss of future tracks during the first series. So they then need to find ways to engage these effects. Overall, many people think that a drone is a rigid body system, but this is not convenient tool. Actually, a drone is a soft robot under high acceleration. Why? Because to isolate the vibrations between the motors and the cameras, we need to use dynamics. Like you see this cycle here. If you push the drone, and this is a recipe to simulate the accelerations that the drone will experience when flying super fast, this purpose will cause deviations in the created arteries between the camera and the body frame. And this systematic errors in the variation that is not impossible to model can cause errors to the CH as the 2 meters. So there are many challenges where you find with obstacles and challenges. Now, Joan pilots nevertheless are staying capable. Nobody are capable. Pilots they are quite slow, they are quite fast at reality, despite the order of the same reaction time. And they can do very quick decision making. Now, a serious supply is that the collaboration need the system to not race in money. In the time we took this video, it was actually 16 years old. And now they start embracing drones at the age of 12. Let me show you a video on money race in our arena. So actually, to do the experiments of this talk, we had to build an arena. I didn't think to the they just whatever. Yeah, right now it's all. And that's then high. Did it? So as you can see, the sport is very challenging because you need to push quantum at the distance. So eventually we will crash because if you don't crash, it means you haven't pushed the weights. That's also why it's very difficult to do agile remediation research because we are crashing many times. Another times I get. We started working on racing in 2016. But the only 2018 we reached something that was actually considered the world best in terms of autonomous movements. And in fact, in 2018, we participated on board the ILO's autonomous zone summit in Madrid. And at that time, our maximum speed was 3 kilometers per hour. Just 3 kilometers per hour. And nevertheless, it was faster than the other boards. 1 year later, it was a team. We participated in the autonomous zone-based challenge Alpha Pilot in Austin, Texas, where our maximum speed was 30 kilometers per hour. So in just 1 year, we were able to improve the speed by a factor of 10. But we realized that we were still very far from pure pilot performance. And there are many reasons why we were far from pure pilot performance. First of all, we were not using components that are used in road racing competitions. So we reached out already at the time to expert road racing pilots and asked by specifications we built a great agile autonomous drone. We call this drone system, which is agile. It's about 20 centimeters diameter. It uses an NVIDIA Jetson TS2 as a brain and an internet sense camera as the eyes. Consider that drone pilots, when they navigate the vision base, they only use one camera, so Swifter will be using only the last camera. We will require the same competition-based experience. Swift is very agile. You can accelerate on 0 to 100 kilometers per hour in less than seconds, making it faster than a Formula 1, which takes 2.6 seconds. And Swifter extends its acceleration up to 5 Gs, which is much more than Astronaut's experience when they are launched from the camera to the International Space Station, which is about 10 photos. And we are already on the coast to the it's around 1.5 Gs. So 2.1 will be on board this one. But besides the hardware equipment, were actually made a difference was the software. So we had to rethink completely the entire hardware. Before the pipeline was designed on the destination, claimed and control it, and we had to change everything. So let's certainly find the autonomous progress problem. What is autonomous progress? With autonomous progress, you want to find the control inputs you often need when you manage the flight time through a series of gates to be passed in a given forward. So what you want for boom is to manage the uptime, which makes you want to be managed this integral in the rest, subject to several constraints, like system dynamics, input constraints, state constraints, physical constraints, and very importantly, perceptual constraints. Why? Because you want the flight to base, so you can only fly trajectories that facilitate the perception task, whether use perception of the destination for detecting the gates, and also because you want to pass in the gates, so you constantly need to make sure that the camera faces the gates above time. But as I told you before, there are single and item-based threats, so we can alleviate them if you actually plan trajectories that reduce the most obscure and dynamic ways. When we started working on autonomous racing problem, we started working not on neural networks, not on machine learning, but actually we worked on the standard classical things, on actual control theory. So we thought of solving the problem by the component from speed planning and so on. So you don't race to have the shit to meet up with the track. You the train and the testing track can be safe. This is what exactly human pilots do. They get access to the track that makes compounds and they practice the track to the real competition. So this means that the track is developed next. The map of the guide is in interpreters. So you can plan an optimal trajectories that passes through all the dates in unit time. And we propose the first component to do so by exploring the entire automated model. How does it work? Watch this animation on the bottom left. You start with a random trajectory, and the algorithm finds the time optimal trajectory. Time optimal assuming that you are perfectly identified in the parameters of the zone, and that the environment is normal, which is also obviously a challenge. The great news is that these algorithms provide the overlap package of the not time. The problem though is that utilization take about an hour, so you could not replan the trajectory in presence of disturbances and drift of the destination. So the key students, when they get the 3 years to develop a replaying in the algorithm, also based on optimal control, in particular on what is predicted controlling control, that allows you to relax our senses and fly optimal trajectories, requiring only 2 milliseconds for replan. So replanning was possible in 2 milliseconds other than 1 hour, but the performance was still inferior with respect to human pilots in the face of another distance and more uncertainty, which are different biggest challenges. We really only need them to forward when 40 years ago, So after working for 5 years on optimal control, 2 years ago, we made the drastic change. Motivated by a teacher student who had been working by reinforcement learning, meanwhile, he showed us that the reinforcement learning couldn't be taught in control. And I will talk about this. It also reinforcement learning that maximizes the task level objective, allowing the scoring of robust control responses and then assisting in settings where the small disturbances could lead to the responding failure. So now, basically, what allowed us to defeat the human cycles was environmental control. It takes us in the state of and out is the control commands. The same control commands are neural packets after on the joystick. Why do we like to resort to reinforcement learning? Because standard controllers are very sensitive to unending effects, like estimation risk and aerodynamics and perception residuals. You see a sector here. The put trajectory here is the guaranteed optimal trajectory that would guarantee superior performance. But this optimal trajectory is optimal, allowing you to connect securely to the manage accuracy. But it will be false people from best of, because you don't tend as much as it's organization systems. So any unnamed effects we need to gauge was for the optimal trajectory. Now, system uses onboard estimation provided by the single onboard camera. How does it work? One user dialog plus a gate-based was estimation. So dialog basically is fixed, as you already know. We treat the also do have motion blue. Here in blue you can see the output, and in green you can see the performance in the middle. The delta that registered the experience is about 20%, which is 10 times more than dialog its notebook experience as long motions. So when you go faster, like a speed of more than 10 meters per second, basically we basically go out 10 or 20%. So 20 meters and 100 meters and current can happen. So yellow was going out. We have to relative yellow with the map-based organization from observation of the gates. So we have a neural network that detects the gates with step parameters. And then we have a algorithm, so perspectives on main points that put hits the position and orientation of the drone with respect to the incident gates. But as you may know, it provides the accuracy that scales quadratically with the distance from the gates. So when you try to map the ellipsoid or uncertainty again, see here, you see that it's actually quite big. And often, this ellipsoid combines with gates, which makes anything problematic. So when you deploy a classic controller, it doesn't work. It just doesn't work. As I said, what we did brought it forward was to use a neural network controller trained with deep model fish, deep reinforcement learning, in simulation. How does it work? In simulation, the drone learns first to fall, then to glide, and finally to race. You see here all the windows of aberrations I have switched to learn how to race or restart. We do so by maximizing a work function that consists of 4 terms. The first term is the progress term. You want to find in favor of policies that maximize the progress over the skill. You also want to favor policies that favor perception awareness, so that for the use motion error, a keep clearly data, all this in the center of the supervisor gauge. Third, you want to favor policies that are continuously with the policies output at the previous state for the various code team really reaching out to get the controller. And finally, you want to penalize captions. So after 7 years of work, in June 2022, made by Tinsidic and World Champions of Robotics. There are 2 major leagues, the non-resident league and the multi-GP international league, and they batted the World Champions of the team. Plus, my team is the basis champion of the list. The important thing to remember is that they used the same hardware. So we built the autonomous drone according to the specifications of the human champions. And the autonomous drone was identical to the drone used by all the 3 parties. They had the same aerodynamics, the same weight, the same size, the same camera, the same field of view, and was the same. The only thing that didn't have was the opportunity, but we balanced the weight of the opportunity with the balance. So it was a well-set race. Then we let the short balance reverse on the racing track about bottom. And we will have to give the new bias the same adrenaline that then they experience in a normal publication related to spec public. So they invited the lady people from the family, friends, students, with about 1,000 people. And now I'm going to show you the video from the view of the human lives. Sister is going to be colored in blue, and the first of the chemicals was Alex Vanilla from the US is colored in red. And so it's data. So switched warmer, and it wore in a new time of 0.5 seconds with respect to the best humor. And it been also reported the majority of needs. It won 16 out of 25 races. Now, as I said, the rate down with 0.5 seconds. Is this a significant margin compared to the performance of the human world champion? Yes, it is significant because in these broadest competitions among humans, the distance between the first and the second place winner is something of 0.1 seconds. Now, was it enough to train simulation? No. What you see here is a fair simulation to reality, but like sometimes visible picture but in this case, Spanish in charts. What you see, the purple, is the trajectory discovered by Swift. And the one in the orange is the one flow in the other world. So in the other world, if they will fly a different trajectory, what? Because of aerodynamic effects and perception with symbols. What about these symbols? Well, the problem is that simulation does not capture all the ideal sequences of the real world. You see, the world is now a data audit. We have a two-word flow. We don't have manual flow. And the forces and torques that it all experiences when it flies at this high accelerations are very, very distributed model. The only way for one is aerodynamic effects in the use a computational redundancy here. We cannot bother them because they can take some hours to date and compute for a simple interference. But also under the simple effects, which I'm thinking the statistical innovation. Remember that I told you that the zombie takes as a soft robot? Well, those systematic errors are impossible to ignore. They can cause errors in the definition of active chemicals. So it was not enough to train the neural network control and simulation, but we had to fine-tune the policies for the augmented cerebral thanks to data collected also in the real world. So this is the takeaway of the initial paper. Simulation is not enough to push robots to the limits of anger, but we need to capture data in the real world. So what we train upon is we're training in simulation. When you deploy to the real world, you are the base of the statements between the technical trajectory and the predicted trajectory from simulation. As I said, these receivers are perception and analytical signals. And they're very difficult to model because they depend on the family state. They are specific flat in the environment. So anyway, there's a standard deploying the learned policy in the real world is that we use motion capture to avoid the outputs. And then we use capture models to model the sensible effects. Then we go back to the simulator. We use discussion models to build the simulator. And then we fine-tune the points in the certain new group simulator. After this is done, we go back to the real world. We deploy now the policy and add a vision-based and the onboard computation onboard sensing in the real world. So we will show that system. This simulation to the Alps initial end is what the lens is to put it against the inbound balance. The takeaway number 2 is there will be one only skill. Environmental controller that was trained in good for silver. We had published several papers in Science Robotics where we showed Davide that I have this optimal control to racing. And we said that this results also extend to other racing environments like candidates. Autonomous Formula 1, for instance, and the Mario was not be done. In this paper, we delve into the reasons of why unfortunately we keep optimal control when pushing robots to the limits for handling. And then the findings are just true. Optimal control proposes the boundary into planning and control. This proposition brings the range of behaviors that can be expressed by the controller. So this means that basically this proposition biases the results of the controller. In contrast, when for standardizing can directly optimize a task their objective, it's a very specific just the lap time. And not only does do that, it also leverages the main blending session, because what we do is that in simulation we inject noise to make the neural network controller able to go from reversing effects that the simulation cannot capture. But these are additional penalization that allows the controller to discover more robust and control responses. So in the data we find combines among other against the protecting type and continue to go. Now, I think whenever somebody's lying with us, that doesn't mean that the other is better off the controller job. No, I didn't say that. What I'm saying is that for racing, other performs optimal control. But still optimal control outperforms iron usual orientation. That's why we're still working on optimal control now. Now, what led the VBI outperform the humans? Which behaviors did in error discover that the human did not discover? Well, in general, DL work because through obviously short trajectories that the human, you can see clearly here on the left, there are 55 shorter paths in group that they go. We'll answer it short. On the right is even more peaceful because Swift has to pass through the top gate and then pass it to the top gate. This model are really significant and it takes years to complete. What you observe is that this human overshoots more than the AI. Pay attention also to the direction of leading on the camera. What you observe here is that the human is least away from the gates before exceeding the holding. Let's use that ways to blow them. Here it's the one here. Versus Swiss, then the human. Now so and you can see, for example, the onboard camera aperture. It's not very standard people because strict security but always the first performer, a half roll followed by half speech. In order to orientate the camera towards the bottom name before passing the top gate. So that's why it's super good. So does it mean now that the game is over? Does it mean that the AI is better than humans? Absolutely not. There are many challenges over time. One challenge is having the robustness. So as you can see, on the field, we had a lot of fun touching those and betting those. But that's where the humans shine. Humans stand generalized to attract and even work out those. For example, in order to verificate humans who are competing in this time, you could get back, control your leadership and control there. So there are still many of the challenges. So the still works only as long as we match as long as match between the train and the problem conditions. We are talking about HDR, motion load of builders, so more until, for example, work in different conditions and people see a training level. But also at the kind of block cost, because that cannot take up, you account wind dusts and a lot of turbulences. Also, we have non-account this. You also belong to points. And by the way, there is an interesting scientific science. At the moment, that system leverages the estimation. But some who are described better quite estimation, they both access from images to put math, which is quite incredible as you can have out. So we'll say the robustness and personally is counterist the challenges. And with this, I would like to thank you for your research.
Thanks a lot, Davide. I don't know if you heard it, but the room gave you a big round of applause, and I can tell you your presentation put some impressed and entertained mimics on people's faces. So, especially your videos and at the end the nice crashes. Let's move on to the questions. Are there some questions in the room? Here we are in the middle. I'll hand over this one. Da, 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 da.
Hello, and thank you for your presentation. I have two questions about your presentation and your work. When do you put a video with robot or the drone that is running and it's pass with a lot of obstacles and pass with the navigation path? I think I want to know how do you use all the output delay in the sensor and the entry in your command law, because you have the camera, you have the EMU, and you have another kind of sensor, and how the robot works or try to fuse all this information to follow a path. This is my first question.
Okay. So let me answer this question then. So the sensor that the utility are a single color Yadani. The sensors are also available on human power control. The only exception is that human power control is not exclusively used solely used by the government. Then the system has a hardware controller and then another controller, like the human power control. So the human power control already controls the body weights and pass. Electric pass and body weights. You can support commands on the joystick. Okay.
Okay.
And då har jag tillsatt på kulturen spinser där bara med två executive plus body centras. So that level control is exactly the same. So your person basically is about the same thing. So the camera that we are using has a 30 hertz. So that means that basically funny difference of 33 milliseconds, and this fixed by the way, which means we need to fine tune also the exposure pattern in a way that is good for the mild. The IMU is at 1 kilohertz.
1 kilohertz.
And we basically do the DIO that relies on 5 signal destination on the state from the natural measurements and the register. This is a slide we were similar that runs on board. But what we realize is that because the images are motion blur, the features are coming from the peripheral wave side. So actually in the end, the DIO was mostly doing inertial navigation. That's why it was different so much. That's why we come to jitter with the gate-based processing. Well, essentially, which is while our paper also by using global information from the map of the magnet. This way is basically the main team's two frames. Of course, there is an additional delay that is due now, but the point of view is single image or grabbing an image takes some signals, and then you need to process the frame. And then you send a bunch of commands. The delay is about 40 milliseconds. 40 milliseconds. As you can see, this delay is no problem because if you remember what I said at the beginning of the presentation, we already offer the human vision system processing and behavior response by the NAVER system is 250 milliseconds. So we are still within the budget of human clients. And also, human models learn to compensate from this delay. By the way, also in optimal control, we were compensating for consumers. But what we found out is that the RL controller is much more robust to uncertainty in this delay is that the optimal controller is. You will find also mistake papers in the paper. So make a call, the delays that are much higher than 40 milliseconds is not a problem. As long as you are below the human power delay.
Okay, thank you. And the second question is about how do you compare the human pilot and the artificial intelligence pilot? For me personally, I think that this compare is not very nice because when like a human, when the human pilot is running a drone, maybe he's thinking about his homework, he's thinking about something. How and for artificial intelligence, I think is only he needs to do one task, and this task is only for that. Donc, for me, maybe this comparing is not good, but do you have another idea, maybe?
So I sketched it. I like this, and I sketched it. So I wanted to read the paper because, of course, we also had to remove the reviewers. So we recorded more than 1,200 trajectories. So the results that I report in these presentations is not just one instance, it's 1,200 instances. You can read the paper, and the figure screen shows all the plots. And you can see that the machine reaches the minimum at all the statistics. Of course, but it's a standard deviation, so the machine is not always pushing on the hills, there is some balance. But we can clearly see in the plots that the box plots is shifted much lower than any other pilot. So it is repeatable. What we also have shown in the paper are structural advantages and disadvantages of humans and of Swift. So as I said, yes, you're correct. The humans, of course, get instructed, they're pocket thinking,
Yes.
investing that money, absolutely. But that's why we document statistics, not just one base, not just 25 grades, statistics of 1,000 other objectives. By the way, they are all released for the public, so people can use them from PIOs now or whatever. So, as I mentioned, that the INU is used, it's critically by three steps in estimations, while humans, pilots, don't use the INU experience. So of course, this is a structural advantage, but also humans had a structural advantage. For example, humans had a conduct from DJI that provided as 120 frames per second, while Swift only had 30 frames per second camera. We also noticed that at the start, the Swift was typically reacting much faster. Of course, it's a machine, so when how does it work in this competition? Very vector, like a shotgun, a gunshot, and then the pilots start. So we introduced a random jitter to make this comparable to humans. We actually measure the reaction time at all by this human, by all these humans, 1,200 seconds. The reaction time is 125 milliseconds, which is still the decent days that action time about 200 milliseconds, because it's all year, by the way. And we so far to this. So in the end, with the mid time of Swift is 0.5 seconds. You see, there is a lot different that is actually due not to the fact that it's faster at the start, but on the fact that it didn't need a scores trajectory that are faster than humans. We did a combination. You will find this in the paper that we did family honest here. At some point, the human pilot from Australia, he challenged Swift and he said, Al, I want to design my truck. By the way, the truck was designed by NAVER, that's human pilot. NAVER was also a former work champion. And then the policy person said, okay, what to design my truck? I said, you put 3 gates, the pilot on the same plane, we turn the best distance to the gates. Then with few errors that were 2 hours, and he made his best performance. We recorded. Then we train the Swift in simulation, we did adjustments, and then the Swift is cool and a better trajectory. So the humans were flying slowly in the blades, while the Swift followed. It was much more efficient to do this slowly, like a babe's ship. They don't how this is just blow it. You can find a lot of videos also in human pilots on personal with TikTok that bit.
Perfect. Thanks a lot, Davide, for this very interesting talk and the very extensive answers of the questions. Very, very interesting. Please, let's give the speaker another round of applause.